Right, so today we are going to start looking at the next design paradigm, which is called greedy design technique. So, like your dynamic programming, greedy design technique is also used for optimization problems, but this is for a different type of optimization problems. So, if you look at your dynamic programming, it is used for what we call the multi-stage optimization problem, which means at every stage you're trying to optimize something. So if you take the coin change problem, for instance, every cell you're filling in refers to some optimal value. So dp of I of j is the minimum number of coins required for some value j using some denominations up to I. So whether it is the last cell in your table or the first cell or some intermediate cell, for that value of j and for those denominations up to I, that dp of I of j is the minimum. So at every stage you are optimizing something. So that problem is called a multi-stage optimization problem. Or if you take your longest common subsequence, your LCS of I of j is going to be the longest common subsequence between the first j characters of one string and the first I characters of another string. So irrespective of whether it's the whole string or the first letters alone or 2 letters, 3 letters, whatever it may be, for those two substrings, you're taking the longest common subsequence. Again, at every cell you fill in the DP table, you are finding an optimal value corresponding to some subsequence. So when you're optimizing at every stage in a problem, it's called a multi-stage optimization problem, for which we use dynamic programming. But for problems where overall at the end you have one final quantity which you have to optimize, and which you're not going to optimize at every stage, we use what is called the greedy algorithm technique. So I'll give you an example. Let's say we have some 10 lectures which are to be delivered in our university, guest lectures or something. So for each lecture, a time slot has been scheduled from X o'clock to Y o'clock, for instance. And there are overlaps. So something starts, let's say, at 10 o'clock and ends at 11. There's another lecture which starts at 10:30 and goes on until 11:30. So there are 10 lectures and the timings have been scheduled according to the availability of the respective faculty. Now we want to allocate classrooms for these lectures to take place. Obviously, if there are two lectures which have overlapping time slots, they cannot happen in the same classroom. But if there are two lectures which are not overlapping, so for instance, if you have a lecture from 10 to 11 and then something from 11 to 12, they can be put in the same classroom. So the first one will happen till 11, and then from 11 to 12, the second lecture can happen in the same room. So this is the problem given to you, and your objective is to allocate classrooms for these lectures such that as few classrooms as possible are used. So obviously, whenever there are two lectures or whenever there are a number of lectures which are non-overlapping, you will try to allocate the same classroom to them. When there is an overlap, you will take a new classroom. That's the logic you will use, right? So in this problem, if you look at it, our objective again is to minimize something, minimize the number of classrooms being allocated. So it is an optimization problem, but at every step, you're not going to be minimizing. So at one step, you'll pick one lecture and you'll allocate one classroom. You'll be like, this person's lecture goes to classroom number 1. This person's lecture goes to room number 2. Again, the third lecture goes to room number 1, and so on and so forth. So in those individual steps, you are simply allocating something. You are mapping one resource to one requirement, for instance. You're not doing any optimization, but the sequence or the collection of mappings that you do, the collection of resource to requirement allocations that you do overall should optimize a certain value. So you have to allocate in such a way that the number of classrooms is minimized. Or to give you another example, similar to that, there are a number of trains which are coming in at a railway station. Each train has an arrival time, and then it will wait for some time in the station and it will depart. So you have to allocate platforms for these trains. So obviously, any two trains which have an overlap in the staying time cannot be allocated the same platform. So you need to do the allocation with as few platforms as possible. So these kind of basically scheduling and allocation based problems, where you will not optimize at every stage. At each stage, you're just going to be picking something and allotting it to something else. but overall your allocation should be in such a way that some quantity is maximized or minimized. That kind of optimization problems we generally use greedy algorithm. So the basic idea behind a greedy algorithm is you choose the local optimum at each step, hoping that it will finally lead you to the overall optimum. So what do I mean by local optimum and overall optimum? So like I said, in a dynamic programming or in a multi-stage optimization problem, you know at this step, this intermediate step, this is the optimal value. So the next intermediate step, that optimum is going to be some extension or some modification of the previous optimum. Here it's not like that. There is no intermediate optimum defined per se. So you will have to define your own optimum in some way, and then at each step you will try to pick that optimum, hoping that finally you will end at the optimum you want. So for instance, coming back to our lecture hall and lecture scheduling problem, your idea could be at every step I'm going to pick one lecture and I'm going to allocate it to one classroom. Like I'll take the first lecture, I'll allocate it to room number 1. I'll take the second lecture. If it has an overlap with the first lecture, I'll put it to room number 2. If there is no overlap, again I'll put it in room number 1, and so on and so forth. So at every step you're going to try, you define some criterion. For instance, a lecture with minimum number of overlaps, or the shortest lecture or the longest lecture. You define your own criterion, and I am going to talk in more detail about what defining criterion is shortly. So you will define your own intermediate optimum, because this is not a multi-stage optimization problem. So the idea of intermediate optimum is not clearly defined. So you will define your own intermediate optimum. At each step you will pick that option which satisfies that intermediate optimum criterion, and you will continue to build your answer, hoping that finally it will lead you to your overall optimum. So the idea here being, because we are going to define or come up with our own definition of intermediate optimum, it's very easy to just define something the way it comes to you intuitively, but you might not realize that the intuitive definition might be incorrect. So you have to analyze the definition you pick, or you have to analyze what you are going to call your intermediate optimum, and you have to make sure whether that will actually lead you to the overall optimum or not. So that is the basic philosophy, and I will make it a little more clear using a quick example, and then we'll move ahead. So we'll talk about greedy choices. So this is called the interval scheduling problem. This is one of the classic problems which are solved using greedy technique. So you have n jobs to be done, J1, J2, so on up to Jn. Each job has a start time denoted by S1, S2, so on up to Sn, and an end time E1, E2 up to En. So obviously the duration from S1 to E1, that interval is the duration for job J1. S2 to E2 is the duration for job J2. So on up to Sn to En is the duration for job Jn. That's the notation. Now our idea is, you want to pick some jobs and perform them. The constraint being, when I am doing one job, any other job which has an overlapping time duration with this job cannot be done. So it's like your classroom scheduling. If one lecture is happening in this classroom, any other lecture which has let's say an overlapping time schedule cannot happen in this classroom. So like that, you're going to pick jobs or intervals basically, and you have to pick as many intervals as you can. Your task is to pick and perform as many jobs as possible. So maximize the number of jobs being performed, subject to the constraint that when you're performing one job, anything that has an overlap with that cannot be performed at all. So in simple words, the question boils down to which jobs to perform and which jobs not to. So for each job, do we perform this or do we not? So if you look at this example here, so each colored rectangle represents one interval. So the time ranges from 0 to 11. If you look at this first yellow rectangle, the interval is from 1 to 4 in time. If you look at this red bar, it is from 0 to 6, and so on and so forth. Now, so let's say you pick this yellow color rectangle, this job. Let's say we are deciding to do this. Now this blue is overlapping, so we cannot do that blue. This red or orange, whatever, this one is also overlapping, so this cannot be done. This one, if you see, does not overlap. This first job ends at 4 and this thing begins at 4. So this one can be done. So we had this yellow, this orange, which we are doing, 2 jobs so far. And now that we are doing this orange, this green has an overlap, so green is rejected. This pink one has an overlap, so the pink is also rejected. This blue job also has an overlap, so the blue one is also rejected. If you look at this grey color one, there is no overlap. This thing ends at 7, this thing begins only at 8, so this can be done. So if you see, we can do this yellow, this orange and this grey, which is a total of 3 non-overlapping jobs. You take any other combination, supposing you choose to do this dark blue thing, then you will see this first one, yellow is ruled out, red is ruled out, orange is ruled out, green is also ruled out. This pink can be done. Because you're doing the pink, the blue and grey are ruled out. So in this case, you'll be doing only the dark blue and the pink. So like this, if you take any other combination of jobs, you will see you can do at most 2 jobs. This over here, yellow, orange, grey, which is I think A, E, H or B, E, H, I'm not sure. So yeah, yellow, orange, grey is the only combination where you can do 3 jobs, and there is no combination such that you can do more than 3 jobs. So the maximum number of jobs that can be performed for this example is 3, and they are the yellow, orange and grey tasks respectively. So this is an example of a problem. So what we did is, we started by picking one job. So in the first case we picked the yellow, and then we ruled out whatever is not possible. Then we picked the next valid one, again we ruled out whatever is not possible. We kept doing that. And then in another case we picked the dark blue, we ruled out whatever is not possible. So you choose one starting point, you eliminate the invalid options, and then you continue doing by that. So there are multiple possibilities, right, of starting point. So depending on your starting point, you can end up with different combinations, and then it is going to be computationally expensive if you are going to try all these possibilities and then see, okay, I've tried every possible combination, this one is the maximum. So you are going to come up with some strategy to help you pick whether to do this or not do this at every step.